Hi everyone, this video is on the sign test for paired data. I'm doing an example of how you work out problems like this, and I will start by just talking about what kind of data we're talking about. So in the example that I have here, we're talking about a marine biologist studying a water treatment process that may or may not have impact on the pH levels of a bay. So the biologist is measuring 10 randomly selected locations both before and after implementing the treatment process. And then the question is whether this treatment has some kind of effect on the pH levels in the bay. So there are 10 randomly selected locations before and after implementing the treatment process. So each individual is tested both before and after. That means that we do for sure have paired data. And then because it's a small sample size and we don't have any information about whether we believe that the underlying data is normally distributed, then this is a good candidate for a non-parametric test. So for paired data, we have two options for non-parametric tests. That is, these are tests that don't require the assumption of normality or a large sample size. So two non-parametric tests that we can use in this kind of situation, the sign test and then the Wilcoxon signed rank test. Now, the sign test is the least powerful of the two, but it really does have the fewest restrictions on it. We can use it for paired data, even if that paired data does not have any kind of normal distribution, and in fact, even if it doesn't appear symmetric. The Wilcoxon signed rank test, technically the data should be symmetric for that one, but the sign test doesn't have any restrictions like that. So we're going to use the sign test for this problem. And here we go, let's look at the data. So we've got the 10 locations and the paired data associated with each of those 10 locations, the pH before and the pH after. So for the sign test, it's really easy. You're going to start off just by putting pluses and minuses next to these rows of data. I'm going to put a minus everywhere that the before is less than the after, and I'm going to put a plus everywhere that the before is greater than the after. So in this first row, since 7.5 is less than 7.6, I'm just going to put a minus there. And then 7.8 is greater than 7.7, so that gets a plus. We get a minus here, a minus here, a minus here on all of these, 7.8 and 7.8. Now here, neither of them is greater, and so I'm just going to skip this one altogether. I'm going to kind of just ignore this data point when they're tied like that on the sign test. So then we have another minus, and a plus, because 7.7 is greater than 7.6. So now we try to formulate the test statistic based on the number of pluses and minuses that we have. The number of pluses I'm going to write as n sub plus, which is clearly just 2. There's 2 pluses. And then n minus is the number of minuses. There were 10 observations altogether in this data set. One of them we just aren't considering at all, and then there's the 2 pluses. So there were 7 left that got minus signs. And then the test statistic we put as a B, and then I always put the S down in the subscript just to show this is the test statistic and it comes completely from the data. This test statistic B sub S is going to be the maximum between n plus and n minus, which of course is just 7 in this problem. Now we're about to take this test statistic to the table, as we always do with test statistics, to figure out the p-value. And before we do, we're going to need to know how many observations there were in total, so that way we can look at the right line on the table. We had 10 total, but actually one of them we're treating as if it's just not even there at all, the one where there was a tie. So we're going to say this is like having n sub d, d for differences, the number of pairs with differences, and that's going to be 9. There are 9 pairs here. So we're going to take this information that the test statistic equals 7, that the number of pairs equals 9, and we're going to go to the relevant table in the book. Here is the table. It's table 7, critical values and p-values for B sub s for the sign test. So we know we're in the right place because we're talking about the sign test. And remember, we said B sub s was 7, and we said n sub d, the number of pairs, was 9. So we're going to have to go on the rows. We're going down to the 9th row because that's where the number of pairs is 9, like we have. And then we're looking for this test statistic 7. So as it says in the text on this table, the numbers in bold type are the test statistic BS. So I have some numbers in bold here. Let me just zoom in a little bit. I've got, those are the numbers in bold we're talking about in each of, in the line here on this row. So I'm erasing those. We need to look at those though and find out which one matches the test statistic that we came up with. Well, we came up with the test statistic equals 7, and so there's only one there that has 7 in bold. You can see that there are a couple of 8s, there's a couple of 9s, but the 7 is the test statistic, and then the thing in italics right there is the corresponding p-value. So the p-value for this test, this sign test, with this data is 0.180. And as usual, we'll just use alpha equals 0.05 as our level of significance, and it turns out that our p-value is larger than this alpha, which means, therefore, we do not reject the null hypothesis. Now, what is the null hypothesis? You'll notice I kind of just skipped over that part when I was introducing this test, and that's because it's not quite as straightforward what the null hypothesis is in terms of symbols. But the idea here is that the null hypothesis is just that the two distributions, so we're talking about the distributions of pH values before the treatment and after the treatment, the two distributions are the same, or alternatively, they are different. So the two distributions are not the same. So we do have evidence here that, we do not have evidence that we should reject the null hypothesis. There is no evidence, or not enough evidence, to tell us that the two distributions are not the same. I'll just make the little comment here that you can see that the null hypothesis and the alternative hypothesis don't say anything about directionality. We're just talking about the same versus different. So for that reason, you can see that the note in table 7 says that this table provides selected values of the test statistic in bold type for a non-directional alternative. So the numbers that we see in the table do correspond already to the non-directional alternative. If we were working with a directional alternative, then we would have to divide our p-value in half. So in the context of this question, no, we do not have evidence that the distribution of pH values is different before the treatment and after the treatment.